So like I said, we're going to be doing rotational and vibrational spectroscopy next, with the goal of creating the spectral simulation of carbon monoxide spectrum. Okay. In order to simulate that spectrum, you need to know about all the parts that go into that spectrum. We're going to simulate not just the peaks based upon the bond length of the molecule and the mass of the molecule, but also how much it stretches, like the centrifugal distortion constant, and then also the vibration and rotation coupling constant. So we're going to be using all of those variables in our simulation, and we will actually produce a very realistic looking row vibrational spectrum. And then we'll be able to compare that to the actual data. And so you'll be able to simulate every peak in that spectrum. And not only that, the fun thing about simulating it is you can then change the temperature and see how it matches. You can change the bond length and see what happens. You can change all of these constants because you're in control of the look of the spectrum. Then you can let Excel do that, and Excel will change those variables until it matches the best. And so this is a way to do what we call spectral deconvolution. And so we're going to get into that advanced technique for extracting physical information from a spectrum. Okay. But in order to do that, we need to talk about some of the basic science behind it. So today we're going to talk about rotational spectroscopy, and then I'll pass out the exams. We can go over those too. Okay, so this is kind of a short lecture on rotational spectroscopy, just to get you started on rotation and vibration. So our rotational quantum number is J, and the energy levels are this B times J plus 1. This B is the rotational constant, okay? And a lot of times you'll see a little tilde on top. It's just hard to do with some of the fonts, and that means it's in wave numbers. And typically in our spectroscopies, we talk about wave numbers, centimeters to -1. Now, this is a structural parameter, this rotational constant. You got Planck's constant, pi, the speed of light, but right here, this is the moment of inertia. And that's where the masses and the bond lengths are, or rotational lengths. So let's look at what those are. So this rotational constant is the moment of inertia, and this moment of inertia is a geometric parameter. It's the masses rotating around the axis, and it's not bond length. Notice this RA is the distance from the axis around which it's rotating. It's not this. Okay. So this moment of inertia is based upon the distance that it is from the axis around which it's rotating. Same with this for water. You know, this, if it's rotating around the C2 axis, this is RH, not this. Okay. But we know if we can use this rotational structure, you know, this physical constant, this rotational constant, if we can determine RH, and we know from RH, then we can get this theta, and so we can get the bond angle, and with that bond angle, we could come up with the geometry of water. So we could figure out what R is by knowing RH and knowing the angles and so on. So we can determine the structures of molecules using these other structural parameters. Now, one thing about this is as light comes in, if light's coming into this molecule and oscillating in this direction, okay, this is a positive charge, this is a positive charge. When I rotate this molecule, what can light interact with? the dipole goes up and down. And so rotating the molecule this way, there's no change in dipole. And so just knowing about the way light interacts, this is a plus, this is a minus, as it's coming along into this axis. It has nothing to interact with. Whereas if it's like a diatomic, and you have a partially positive end and a partially negative end, and you have that dipole, then light has something to interact with. And so let's we'll explore that some more in a minute. Let's think about the energy landscape. So if we have electronic energy levels, that's our UV-Vis spectra. So you should know that, UV-Vis transitions are electronic transitions. If we zoom in on this ground electronic state, we'll have the vibrational levels. I just showed 2 vibrational modes here. There's 3n-6 of them. And so those are going to be labeled with their various vibrational quantum numbers. If we go into any one of those vibrational quantum number levels, okay, those transitions occur in the infrared typically. If we go into any one of those vibrational levels, we can see the rotational levels. So you see the rotational levels are really close together compared to vibrations. And they're invisible in terms of the electronic transitions. So this is an idea of telling you what kind of energy differences we're talking about. And the rotational transitions occur in the microwave. So really low energy photons. In fact, that's why a microwave oven is called a microwave oven. So there's a microwave generator in there, and it's tuned to water. So it's tuned to the absorption of the rotation of water. That's why your water gets so hot in the microwave, because that microwave energy is absorbed by water. And a lot of other molecules that happen to absorb that same kind of energy. But it'll go through plastic. Plastic doesn't absorb microwaves. You got these long polymer chains, the CH2s. They just don't vibrate or oscillate or twist at those frequencies. So microwave light goes right through your Tupperware plastic container and hits the water in your food and flashes it to steam, and then that steam steams your food. And that's called a microwave oven because of the frequency of light that is being emitted into that. So it's kind of funny. A friend of mine in graduate school, this was 1992, and he came from Moscow University, and they had an international student dorm, and I go to see his place because I hadn't been in the international student dorm. And he says, my freezer's broken. So he had a fridge with a microwave on top, little single unit. You've seen these things, little fridge on the bottom and a microwave on top. And he opens the door and he said, my freezer's broken. And I said, it's not a freezer. It's a microwave oven. And he said, really? And then I said, yeah, you punch these buttons or whatever. So he punched the button and and then he stops and opens it up and sticks his hand in there and he goes, my oven's broken. I was like, no, it doesn't heat up inside. It's not that kind of oven, So the microwave oven, is different, right? The box doesn't get hot. It's a radiative oven. Radiation is going in there and heating your food by the rotation of water. That's pretty neat. Yeah. Yeah. So, he's a brilliant guy, but he just never seen a microwave oven in 1992. Yeah. So yeah, light must be able to interact with that rotating molecule for absorption to occur. Therefore, this is in the gas phase, okay, that molecule must possess a dipole moment. And all polar molecules possess those dipole moments. So we're going to need those skills that we have of Vesper shapes, right? Drawing out a Vesper shape and knowing if it's polar or nonpolar, right? So ammonia is polar, but BH3 is nonpolar. NH3 is polar because it has that extra lone pair of electrons, and it's a trigonal pyramid. BH3 doesn't have those extra electrons, and it's trigonal planar. And since it's trigonal planar and the H's are at 120 degrees, all of those little bond dipoles cancel each other out, and you have a nonpolar molecule. And then the selection rules are delta J plus or minus 1. Now, to answer the question why, it's because light has 1 unit of angular momentum. Okay, and I always was frustrated by that because in our vibrational transitions, we use the transition dipole moment integral to come up with our selection rules. Particle in a box, transition dipole moment integral for our selection rules. But when we got to rotation, everybody just talks about angular momentum. It's like, where was angular momentum before? You know, where did this come from, this argument? And so light has one unit of angular momentum. That angular momentum can be added to the rotation of the molecule to cause it to rotate faster. It can come in and slow the molecule down if the angular momentum is in the opposite direction of the rotation. And so that would be a delta J minus 1. Raman is a 2-photon process, and so you can have +2 or -2 or 0. They can cancel each other out. Okay, so we have that illustrated sort of here. But I didn't like this idea of the angular momentum argument. There's nothing really wrong with it, but I thought, can I use symmetry? And so I had a graduate student, Victoria, and I said, would you go and find the papers or the textbooks that talk about the symmetry selection rules for rotation? And there were none. After all these years, you know, we've known about rotational spectroscopy for over 100 years, and we couldn't find a single paper that talked about the selection rules, delta J selection rules, using symmetry in the particle on a ring. And so we wrote the paper up, and yay, and that was part of her thesis, and so she graduated. So, so you know, it's really fun to do that, and this is just a picture of the rotational wave functions, and we can go into this, and we will go into this more in the future. So, but you can get the delta J values or delta M's in this case based upon symmetry, and it's really fun. Now, let me re-emphasize the two diagrams or two plots that we always show. We show the energy level diagram, and so that's really important to think. The energy levels, okay, are all the energy levels plotted, but we really can't detect levels by themselves. We have to detect differences. And so it's the differences in these energy levels that give us spectral lines. So in the spectrum, we have lines. So knowing the difference between lines and levels is really important. So these are the spectral lines in increasing energy, okay? And notice as the difference in energy level grows, so does the position of the spectral line. Okay. So this is a big difference in energy here. It's a long arrow, and so it has a high frequency here. This is a really short distance, a really short arrow, and so it has a low frequency. Okay, and so these are all spread out in the spectrum because there's differences in the energy levels, and they're not constant. They grow as we go along. Now this energy plot is not to scale because it goes up as J squared. And so these spacings are not far enough apart. You know, it's not accurate is what I'm saying. The concept is right, but this energy level diagram should really go up quicker than that. These spacings should be much further apart than these.
So it's kind of like the semi-large scale.
Yeah, maybe that. Yeah, it's just definitely not a linear scale in this particular plot.
So why is the intensity, I guess the intensity largest in the center?
That's a great question. Boltzmann factors. Okay, so this is a good question. I think I show it in this set of notes. Let me see if there's a better one later on. Let me just zoom ahead. No, there may not be. Okay, let me go ahead and answer that right now then. Okay, so the degeneracy of these particular levels. So remember the Boltzmann factor of J and T is equal to G sub J e to the minus E J over KT. Is everybody clear on that? Boltzmann factor? Okay. Now G sub J is equal to 2J plus 1. So it's a function now. And it's a function of the J quantum number. And in fact, you know this function because, again, it's rotation. And what are the atomic orbitals? What is the quantum number that tells us the difference between an s orbital and the p orbital and the d orbital? It's L, but what do we call that? Angular momentum. What is angular momentum? That's rotating. Rotating. And so it goes up as 2L plus 1. So the s orbital, 2L plus 1, the s orbital has an L of 0. And so 2 times 0 plus 1 is equal to 1. Okay. Oops. But then the p orbital, oops, L equals 1, 2L plus 1 is equal to 3. Okay, so this right here is our degeneracy for our rotating systems. In our rotating electrons rotating around the nucleus, 2L plus 1 degeneracy. We get to the d orbital, it goes S, P, D, L equals 2. 2 times 2 is 4, plus 1 is 5. We have 5 d orbitals. F orbital is 3. 2 times 3 is 6, plus 1, that's 7. 7 F orbitals. So we know about this degeneracy of rotating things from our atomic orbitals. Same thing for rotating things when the whole molecule is rotating. Okay. So the rotational, it's kind of weird, the rotational wave functions look like the atomic orbitals. Yeah. So that's kind of bizarre, but that's what that wave function looks like. It's the same functions. And so this degeneracy, notice as J goes up, there's more places to put molecules. And this is a statistical thing. If I have 7 chairs in level number 2 and I only have 3 chairs in level number 1, no, I have 5 chairs in level number 2 and 3 chairs in level number 1 and 1 chair in level number 0, and I say everybody grab a seat, statistically there's going to be more people in level 3 because there's 5 places to sit. There's only going to be 3 people in level 2 or level 1. I'm getting the numbers mixed up, but there's going to be more people in the places that have more degeneracy. And a spectroscopy is statistics. If I send light through the molecule, the intensities are going to match the populations. And so this rise right here is the 2J plus 1 rise. You see how as I go up in J value, this J value, this level here has more molecules in it because of the degeneracy. This one down here only has 1 molecule in it by comparison, right? So this peak right here going from this level to that level is going to have more molecules that can absorb. And so it's going to be more opaque. As the light goes through, there's more chances that it will be absorbed because there are just more molecules in that level. And that's the degeneracy effect. But eventually you get to the exponential piece, which says, all right, my energies are getting too high. At this temperature, I don't have enough molecules that are that high. So up here, I've only got 3 molecules. Because
a lot more space than just not many that can get there.
Yeah, they just can't get there at this temperature.
Right.
And so then this drop off here is the exponential decay of the e to the minus e j over t, kt. Isn't that cool? And so the shape of this is temperature dependent. So if I increase the temperature, I put more molecules in the upper states, and so this envelope shifts to the right. And if I cool it down, I can collapse it down to where just the first few rotational levels are populated. So we can actually solve for it, and we will. That'll be definitely a homework problem. Is what is the J max value? J max as a function of temperature. Okay, so you can actually take this Boltzmann distribution and take the first derivative of it, set it to 0. So where does this thing curve over, and solve for J as a function of the temperature. So it's pretty fun. All right, and so this spectrum gives many measurements of J because we have every one of those spacings is spaced by 2 times the rotational constant, and we'll prove that in just a second. So we have really good average and standard deviation. We've got good bond lengths and angles, but there's 3 rotational constants because there's 3 axes around which we can rotate. And so if you have a lot of different bond angles and bond lengths, you have a hard time getting the structure of the molecule. But this was in the early 1900s, the game. This was like cutting edge research was actually getting the structure of molecules. And they would use different spectroscopic tools like rotational spectroscopy to determine what is the carbon-hydrogen bond length, what is the carbon-carbon bond length, typical, you know. And this was, before we got into X-ray crystallography, this was the way they were solving structures. Yeah. And so that was pretty exciting times, I guess. I wasn't there. But we had, you know, a lot of neat spectroscopy being done at the time. And now symmetry helps. Notice in ethane, we've got, you know, 1, 2, 3, 4, 5, 6, 7 different bond lengths. And 8, 9, 10, 11, 12, 13. You add in the angles, 14. You know, we've got a lot of degrees of freedom. I counted up 14 different variables. And we're only going to have 3 rotational constants. So we can't solve for 14 variables. But symmetry does help. There's only 1 carbon-carbon bond. There's only 1 type of CH bond. And there's only 1 really umbrella angle for those methyl groups. And so I could knock this down to 3 variables, the carbon-carbon bond, the carbon-hydrogen bond, by setting all those things equal to each other, and then setting this sort of methyl umbrella angle. And then I would be able to solve for the structure of ethane using this technique. If I had a 4th variable that I couldn't solve for, I could get a different rotational constant if I did deuteration. So what does putting a neutron on a nucleus do to the spectroscopy? Okay, it changes the rotational constants, okay, but it doesn't change the bond lengths or the bond angles. Why? Why do the bond lengths and angles not change by putting a neutron in a nucleus?
So it's the electrons that do the bonding.
Yeah, it's the Coulombic charges, the protons in the nucleus and the electrons that give you the bond angles, not the neutrons. And so you can do isotopic substitution and get 3 more rotational constants. So it's still ethane, but it's going to have a dramatically different rotational constant because the masses have changed, but the bond lengths haven't changed, and neither have the bond angles. So that's pretty fun. Okay. So then we've talked about Raman spectroscopy and Rayleigh scattering. It's also useful in rotational spectroscopy. We have the incident photon and the scattered photon. We have the Stokes shift where there's a excitation in the rotational levels, and an anti-Stokes shift where there's a relaxation in the rotational levels. And so here's the Raman, pure rotational Raman scattering spectrum. And the big difference is for Raman, you're dealing with the electron cloud, not the dipole of the molecule. And so you don't need a dipole for light to interact with it. So you can do pure rotational Raman on homonuclear diatomics like nitrogen and oxygen. You can't do pure absorption spectra in the rotational region with anything that does not have a dipole. So oxygen's transparent, dinitrogen's transparent, microwave light goes right through those. And that's really vital for our survival. If microwave light didn't go through our atmosphere, which is primarily nitrogen and oxygen, we'd have a runaway greenhouse effect and we wouldn't be here. The Earth would be like Venus, okay, which is so hot because of the greenhouse effect. Okay, so we have been blessed with an atmosphere that's mostly homonuclear diatomics. and the microwave light that needs to leave our planet can leave our planet. And that's the whole thing about global warming is if we put polyatomics in there, things like methane, CO2, water's really the thing that governs the temperature of our planet. Adding more CO2, adding more methane, adding other kinds of solvents that are non-reactive with oxygen can build up that greenhouse effect and block some of that light that needs to leave. Okay, and so that's what we're talking about, global warming and its atmospheric effects. That's what's driving it. It's really the greenhouse effect. They've changed it to climate change so that they could complain about cold fronts and things like that, but we're not worried about the planet cooling down. We're worried about it warming up. Okay, so for political reasons, they changed the name. It's pretty clear. So then we have the scattering selection rules, and we can do pure rotational Raman. So let's look at some of these transition equations. Notice that you have the Rayleigh scattering, and it's scattered at the wavelength of the laser, but the Stokes scattering is the wavelength of light laser minus this rotational structure. And because it's a delta J minus 2 for the, plus 2 for the Stokes scattering, you end up with this change of 4 times the rotational constant. And then if you do the anti-Stokes, it's a delta J minus 2, and it's also 4 times the rotational constant. So the reason I'm focusing on these rotational constants and their multipliers is that if you're given a spectrum and you know it's infrared, those spacings between those spectral lines is 2 times the rotational constant. But if you're given a Raman spectrum, it's 4 times the rotational constant. You have to know that because the units can't tell you that. You know how most of our problems, you can use the units to figure out whether your answer is right or not? Not in this situation. That 2 or 4 is a unitless value. So you really have to know which spectrum you're dealing with, and you have to know what the spacing in those lines are, because there's no unit associated with that, and you would be off. So this is the transition equation. This is just a review. If we wanted to know derive this 2B spacing in our spectrum, let's solve for the transition equation for delta J plus 1. So this is how we set up the transition equation. Our delta E value is going to be the energy at that excited state minus the energy at the lower state. And so we just put that J plus 1 in there wherever there's a J. And so J plus 1 goes in here and here. So that's what's going on here. B times J plus 1 times J plus 2. See that? And then you subtract the regular energy equation. And then you just do the algebra. Okay, so you just multiply those two together and multiply the B through, and you end up with some things canceling. The squared terms cancel out. So this guy's gone, and with that, we can collect. Here's 3B minus 1B. Okay, so this changes the 3 to a 2. And we have a 2 there. We can pull that 2B out and have J plus 1. So the J goes there, and the plus 1 goes there. And so just to refresh your memory, that B value for a diatomic molecule has this reduced mass in it and the bond length. So there's our structural information inside B. This is telling us then that those rotational lines have that spacing of 2B. How do I know that? Well, I would label these as J equals 0 to 1, and this is 1 to 2, and 2 to 3. You see how each one of these transitions is labeled by this lower J value. So I would label this one 0, 1, 2, 3. And so going from this transition to that transition, that spacing is 2B. So right there, that spacing. And the spacing between the next line is 2B. And the spacing between the next line, and so on. Okay, so for the Stokes transition, we put a J plus 2 in there. Do the algebra. Okay, once again, the squared terms cancel. I've got a minus J here. Sorry, this minus J and the 5 becomes a 4. And so I have this 4B here and a 6B there. If I pull out a 4B, how do I get 4 out of 6? Well, I can simplify that and make it 3 halves. And so it kind of looks like this, 4B times J plus 1. This is 2b times j plus 1. This is 4b times j plus 3 halves. And so it has the same structure. We even saw this in our particle in a box structure. And so for the Raman spectrum, we have 4b spacing between those lines. Okay. So are there anything that I need to clarify? That was a good question about the intensities.
I got one more. So in this equation we talked about bond length. So is this only diatomics?
Yeah, for this particular, actually, these equations are not just for diatomics, but I inserted that B for a diatomic. Okay. Now, let me go back here to some of these bigger molecules. Okay. This, for a diatomic, like our carbon monoxide, that's the z-axis, right? We have the x-axis and the y-axis. And so we can rotate around the x, we can rotate around the y. But you see how, because of the symmetry of the molecule, rotation around the x is the same as the rotation around y. And so, and then rotation around z is not defined. And so if you do a Gaussian calculation on carbon monoxide, you're going to have your rotational constants, and it'll be, so it'll be like 1.93, 1.93, and then I think it puts asterisks for the third because it's not defined, okay? And it labels those A, B, and C. And for a symmetric top, A is equal to B, and C is not defined, or is a different value. And so for a diatomic, since A is equal to B, they just use B, because B and A are the same. And so for our carbon monoxide spectrum, we're really rotating around both axes, and we can't tell which one we're rotating around. It's just a single rotational constant because it's a symmetric molecule. Okay. For water, RZ is not equal to RY, is not equal to Rx. And so you'll have three different rotational constants. A is not equal to B, is not equal to C. And so that's why that when we show it next time, that row vibrational spectrum of water is so confusing, because we have three row vibrational spectra on top of each other, and we can't see the pattern very easily. You can assign it, but it's very difficult. And honestly, you can't assign it based upon a single quantum number like J. You're going to have different quantum numbers for those three different rotations. And the equations work out best to where those quantum numbers are not independent of each other. So you have one principal, like total angular momentum quantum number, and then the other quantum number is actually a difference of the other two. And it gets really confusing. That's one of my bucket list items, is to actually go through the row vibrational spectrum of water and assign it. Okay, I just never had the days and days it would take me to figure it out. It's been done. It's in Hertzberg. You can go through and hack through the math, but it's so intimidating. I've never been able to do it because I've just always had other priorities. But that's one of the things I want to do. Is I want to take that row vibrational spectrum of water, which you'll see next time. It's just ugly.
And adding one more atom to it just makes it that disgusting of a math.
It does. And so even though we're in graduate school, we're still going to just stick to that diatomic. Yeah. I can show you a spectrum of methanol, though, that really threw me. I was just doing regular infrared stuff on solids and liquids, right? And I look at a spectrum, and I had this beautiful rotational structure, things that look just like this. I saw these beautiful resolved rotational lines in my infrared spectrum, and I've got a liquid sample in there. And that's the thing, you're not going to get these resolved rotational lines in a liquid sample or in a solid sample. You have to have a free molecule so it can rotate in space. And I thought, what is going on? And it was a symmetric top. It was beautiful. And I could see the P and R branches. and they were resolved. And we'll learn what those are next time. We're a little ahead. But it ended up being methanol. Yeah, I had just cleaned the spectrometer, the little ATR with methanol, and I got a little overzealous and sprayed it on there. Instead of spraying it on the wipe and wiping, I sprayed it on the ATR, and it went down into the spectrometer, and inside the little tube, I had methanol gas, and it was giving me the PNR branches of methanol. But methanol is not a symmetric top. It's a CS molecule at its best, and C1 a lot of times else. If you rotate that OH group out of the plane of one of the CH bonds, it's just C1. No symmetry. Why is it a symmetric top in the infrared? What's going on? It's behaving like a C3V molecule, and it's not C3V. Any ideas? Y'all are grad students. You can think through this. How can you get methanol to act like a C3V molecule? Or how can you justify that it would?
Probably wrong, but so you have that OH on the top that has free rotation about it.
Yeah.
I'd say that it rotates at such a thin that at any point there's an even distribution of molecules that it acts like it's a solid up there.
Yeah.
And so
that's one of the arguments. It's the internal rotation of that OH. That hydrogen is just smeared around. That it's sort of a symmetric wave function of that OH. That hydrogen around that oxygen is just symmetric, and it gives you a threefold molecule. But that doesn't fit with local bond theory, balls and sticks, where you draw the hydrogen here, and here's where the hydrogen is. It's just smeared around that oxygen, and it's a symmetric top. That's not Lewis dot structure, though. That's not a Vesper shape, right?
we know that stuff is wrong anyway.
Because of the low pH of the oxygen.
Because of what?
The low pH of the oxygen is exact pressure on the adjacent hydrogen. So it's, which makes them to look as if they are like kind of ammonia.
Yeah, it's like an ammonia molecule, it's C3V. Yeah, and so those that methyl group on that end, if I just look at the methyl group, it's definitely a symmetric, threefold symmetry. But that OH, the H breaks that symmetry. And so if that OH is smeared around, like delocalized around that oxygen, then the molecule becomes symmetric. It behaves symmetric. Now, that's one way to think about it. The other thing is to realize what we're looking at is the effect of the rotational constant. And the rotational constant depends upon masses. And that hydrogen is really light. And so this is what we call a coincidental, is another argument. It's just a coincidental symmetric top. That hydrogen off axis of the oxygen doesn't change the rotation of the whole molecule. And the whole molecule has three rotational constants, but two of them are equal to each other. And the third one is different. So the spinning of the molecule around the CO axis is a big rotational constant because you're moving light masses. The masses are in the denominator of the rotational constant. Let me find the rotational constant. Oh yeah, that's right here. See, those masses are in the denominator of the rotational constant right there. And so putting that hydrogen or spinning those hydrogens around the CO axis, that's a really big rotational constant because they have the smallest masses moving. And so that's a big rotational constant. The other is the carbon and the oxygen, the methyl and the OH rotating around each other, around the x-axis or the y-axis. And those are big masses. And so that's a really small rotational constant and not resolvable. And so I'm resolving the big one that's resolvable, and the smaller ones are not resolvable. So that's a third explanation as to why I saw the structure in the infrared. Yeah. Okay, we've got just a bit of time, so let's go through our examples.